We have seen that random variables have probability distributions. There are distribution types that occur often and have their own name. One such special distribution is the binomial distribution, and it is something we have looked at already several times without naming it in that way so far. The model for the binomial distribution is an urn with marbles in it, and a part of them are red. We now sample a certain number of these marbles with replacement, and our random variable x is the number of red marbles obtained. So x is a random variable, it has a probability distribution, and this probability distribution is called binomial, with parameters n being the number of marbles sampled and p the probability of sampling a red marble in one go. This means the percentage of the marbles that are red. This model is very flexible and can be applied to real-life situations often. So let us look at an example. The police makes a control for alcohol for drivers, and let us assume that 2% of all drivers are drunk, and the police now stops 1,000 drivers. Well, how many drunk drivers will they find? This is the random variable x, the number of drunk drivers that they will find. The urn, well, it contains non-drunk drivers and drunk drivers. The drunk drivers are the red ones, the red marbles. It's 2% of all the marbles are red, 2% of all the drivers are drunk. And we sample now 1,000 times from that urn with replacement. That's exactly the model that corresponds to what the police does in this context. In example 1, we have an urn with marbles, and 1/5 of the marbles are red. We now sample 6 marbles with replacement, and let x be the number of red marbles sampled. And we want now to find the probability distribution of x. So, for example, let's find the probability that x is equal to 2. You can find it on your own, and then find also the probability that x equals k. So any number, you can find that on your own. Stop the film, and here comes the result. The probability that the first marble is red is 1/5, and that the second marble is also red is 1/5 to the power of 2. The probability that the third marble is not red is 4/5, and that all the 4 next marbles are not red is 4/5 to the power of 4. We have to multiply these probabilities. This is now the probability that the first 2 marbles are red and the next 4 are not red. We are only interested in that any 2 marbles are red and the other 4 not red. So we have to look at all the different possibilities in which way to get this result. Well, we sample 6 times. 2 out of these 6 times should be red. So there are 6, choose 2 possibilities, and we have to multiply by that number. And looking now at the probability that x equals some k, well, the probability that we get the first marble is red is again 1/5. That the first k marbles are red is 1/5 to the power of k. The probability then that the next marble will be not red is 4/5. The probability that the remaining 6 minus k marbles are not red is 4/5 to the power of 6 minus k. And we're sampling still 6 times, and out of these 6 times, k times we want to sample a red marble, so we have 6 choose k possibilities to get that. So we have to multiply by that number, and we get this formula here. Well, inserting now for k the different values 0, 1, 2, and so on, we find these probabilities here, and the probability distribution is shown graphically in this graph. Now generalizing this formula here, saying that not 1/5 of the marbles is red, but just some part p is red, we get here a p, and this is then just 1 minus p. and we sample n times, not 6 marbles, but n marbles. So here we have n choose k, and here we'll have n minus k. And that's the way that we get now the formula for the binomial distribution. If the random variable x is binomially distributed with parameters n and p, we write this in this way, then the probability of x having a value k is this here. And as we said before, we have used this probability already many times. A different but equivalent model for the binomial distribution is described here. We have an experiment with two possible outcomes, namely 0 and 1. And the probability that we'll get a 1 is just p. And now we repeat this experiment several times, n times. And we count the number of 1, so we add up the number of the outcomes. And then this x, being this sum of the outcomes, is again binomial distributed, because it corresponds exactly to these marbles here. Just the marble, instead of having red, we have a 1 and the others are 0. And we don't count the ones, we just add all the results up. Well, that's the same like counting the ones. So it's just sometimes helpful to know that you can look at the experiment also in that way, and you see, oh yeah, it corresponds to this way of looking at it. So I know the random variable x that I'm looking for is binomially distributed. Let us now solve example 2, and when you read it, you should realize this is something we have done already many times. Just this time we sort of have to think much less. We can reuse directly the formula, but we can also do it from scratch. Let x be the number of scores, and then x is binomially distributed with n equals 10 and p equals 0.9. Why is this the case? Well, it is the same like if we had a urn with marbles and 90% of them were red, and we're sampling 10 times. What is the probability then? What is the probability distribution for x being the numbers of red marbles obtained? The other way of looking at it, in each score, the outcome can be 0 or 1, 1 being a hit or a score. So, and we repeat that 10 times and sum up the number of scores. So again, binomial distribution, n times 10 times, and probability of a 1 is 0.9. So now solve A, B, and C on your own. Stop the film, and here comes the result. So in our experiment, the n is 10, p is 0.9, and 1 minus p is 0.1, and we can now apply this probability. So the probability that Jorge hits exactly 7 times means the probability that x is 7. We insert now the numbers in here with k being 7. We get this formula and we get this final value. Note that if we didn't know about the binomial formula, what would we have done? Well, we would have said the probability that he scores in his first time is 0.9, that he scores in his first 7 times is 0.9 to the power of 7, then that the next attempt will not be a score is 0.1, the probability that the next 3 attempts will not be a score is 0.1 to the power of 3. So this probability here, the multiplication of these two probabilities, is the probability of him first hitting 7 times and then not scoring 3 times. But we're interested only in just in general him scoring 7 times and not scoring 3 times. So the order doesn't matter. The number of possible orders, well, he's attempting 10 times. 7 out of these 10 times he scores, so this means there are 10 choose 7 possibilities, and we get this formula in that way as well. The probability that Jorge scores at least 8 times means the probability that x is larger or equal to 8, which means this is the probability of x being 8 plus the probability of x being 9 plus the probability of x being 10. Again, inserting into the upper formula here, we get these three expressions. Note that here 10 choose 10 is just 1, 0.1 to the power of 0 is also 1, so what we get is 0.9 to the power of 10. Well, obviously the probability that he scores all the 10 times means just he scores in the first go, 0.9 probability, in the second go as well, and so on, 10 times, 0.9 to the power of 10. Also, the expression for scoring 9 times simplifies because this here is just 10 times. There are 10, if he scores 9 times, this means that there is 1 time where he does not score. Well, out of the 10 attempts, there are 10 possibilities for which one is the one where he does not score. To find the probability that he scores at most 8 times, well, we could add up the probability of scoring no time, x equals 0, plus the probability of x equals 1, and so on until x equals 8. Well, simpler is to say use the complementary event, which means the probability that he scores more than 8 times, so x being larger than 8, and saying it's 1 minus this probability. And we get now this expression here. We have found these two up here for x equals 9 and x equals 10. I've written them here a little bit simpler, and we get the final result 26.4%. To find the probability that this binomially distributed variable x has the value 7, we use this formula. However, we can use a simpler way when using our calculator TI-30X Pro. Namely, there is this start register distribution, and 4 is the binomial PDF, so we can find then the probability that x has some value x, and let's look at that. And the second, we'll look then also at the so-called binomial CDF, cumulative distribution function, which is then the probability that x is smaller or equal to some given value x. So we find the command in the following way. Second here, data, so we get this start reg distr. Then we have to go to the right to go to distr for distribution. And then when we go down here, the number 4 is the binomial PDF. This is what we want, so enter. A simpler way is just to enter from the beginning just a 4. And then we can either say that we want to find the probability for a single value, k or x, or that we want to find it for a whole list or for all possible. Let's here choose now the single value. So first we have to enter how many trials we want. In this case, we want to have 10 trials, so that's correct. The probability of a success, our p, is just 0.9 as written here, so enter. And here the small x is now the probability of this random variable being what value do we want to know. This is the value that we have to enter here. The 7 is already in here, so it's okay. So then let's calculate it, and we get that the value is 0.057. If we want to find the probability that x is smaller or equal to 8, we can use this binomial CDF here. We proceed the same way as before. Second data here, we need distribution, and now it's the number 5. That's the binomial CDF. Enter. Number of trials is 10. The probability of success is still the 0.9, and we want now the random variable to be smaller or equal to 8, so we have to enter 8 here, and let's calculate it, and we get the final solution 0.264 as before. Now let us look at the practical application of the binomial distribution, namely at airplane overbooking. The airline knows that on average 7% of the booked passengers do not appear at the airport. They are so-called no-shows. If the airline now has an airplane with 110 passenger seats, it wants it to be optimally filled, so it will overbook it, knowing that a part of the passengers will most probably not appear. This is obviously good for the profit. On the other hand, it is bad for the reputation, and so also bad for the profit if passengers have to be left behind. This means if less passengers do not show up than it was expected, too many passengers show up, and there are more than 110 passengers that want to fly. So the management might decide that the overbooking should be such that there is a chance of at least 95% that there will be no need to leave any passengers behind. So you want to overbook as much as possible, but so that the probability that you have to leave somebody behind is less than 5%. So let us say we book 120 passengers on the flight. There is for each passenger a probability of 7% of not showing up. So we have 120 times the experiment of a no-show, a 1, with a probability of 0.07. However, there are assumptions when we now say this is a binomial distribution. First of all, is it really realistic? But we'll assume it, that the probability for any passenger is the same and that there are no different classes or types of passengers. And the second one is we assume that the 220 passengers are independent, that the 120 experiments are independent. There is no influence of the outcome by the outcome of the first experiment on the outcome of the second experiment. When we throw, for example, the dice, or we assume also that when Jorge hits the in his attempt he scores, it doesn't make a difference whether he scores the next time as well or not. However, with the passengers, probably that's not a very realistic assumption, because typically there will be also passengers flying in pairs or at families, and if they don't show up, well, typically not only one will not show up, but more of them. Nevertheless, we'll simplify now all this and assume that all the passengers are independent, so that we get at least a first approximative idea. So n is the number of booked passengers, for example 120. P is the probability for each passenger to be a no-show, so 0.07. And this means the probability that he will show up or he will not be a no-show is 0.93. And let now the random variable x be the number of no-shows for a specific flight. With the assumptions above, the x is binomially distributed, and namely with binomial 120 0.05. Now, what is the probability that a passenger has to be left behind if the probability for a no-show is 7%, as we said above in the example, and the airline decides to book 113 passengers on the flight? The x, the number of passengers that do not show up, is binomial 113 0.07. So not to have any passengers left behind means that the number of no-shows must be at least 3. If less than 3 are no-shows, so only 2 no-shows, this means that 111 passengers show up, and we would have to let at least 1 passenger behind. So x has to be at least 3. Well, probability of x being at least 3 is 1 minus the probability of x being smaller than 3, so x can be 0, 1, or 2. And now we can calculate these probabilities using the formula for the binomial distribution. This here is just a simplified formula for x equals 0, and here for x equals 1. Actually, if you want, here you have a 1 and up, and this is n, choose 1 here. And then summing up these 3 probabilities, we get 0.0125, which means in the end we have a probability of 98.75% that we do not need to leave a passenger behind. We have learned that the function assigning to each k the value of the probability that x is equal to k is called the probability distribution function of x, or PDF. Here we have this probability distribution function corresponding to the binomial distribution for n being 113 and p being 0.07. So when we want to know, for example, what is the probability that x has the value 12, well, we can read off the probability is almost 5%. Now there is a second distribution function. It's called the cumulative distribution function, and it assigns to each k the value of the probability that x is smaller or equal to k. So here, this graph shows now the cumulative distribution function for the same probability distribution, the binomial distribution with n being 113 and p 0.07. So if I ask now, what is the probability that the x will be at most 10, for example? Well, we can read that off immediately here. And we see the probability that x will be 10 or smaller is a little bit more than 80%, or maybe 82%. We could obviously read that off also here by summing up all these values here on the left. So this is done already here on the right, and the cumulative distribution function always starts at 0, and then it increases only until it ends up at 1. On the next page, the graphs of the probability distributions are shown if the airplane books 114 passengers on the flight. The probability for a no-show is still 0.07. Since we have booked 114 passengers, we want to know the probability that at most 3 passengers will not show up, because then we have a problem. We need at least 4 passengers to show up. Well, 3 passengers or less to show up, we see that here. Oh, that looks tight. Well, we can sum it also up here, which means it's the sum of these 3 that may, or 4 actually here, so that may be 5% or not. We have to look at a table to know that more correctly. This table here shows the probability distribution function and the cumulative distribution functions for n being 113 and n being 114. For example, here we see the probability that x is equal to 6 if n is 113. Here we see the probability that x is smaller or equal to 9 given that n is 113, and similarly here on the right hand side for n being 114. We're interested in the probability that the x, the number of no-shows, is smaller than 4, which means the probability that x is smaller or equal to 3. We have 114 passengers, so we're in this part of the table. We want x being smaller or equal to 3, so we get 0.0379. So 3.8%, which is less than the 5% that is the maximum that we admit. So it is still okay to book 114 passengers. Question, is it also okay to book 115 passengers? So this means that we have to find the probability that we have to leave a passenger behind if we book 115 passengers on the flight. Do that on your own, stop the film, and here comes the solution. Leaving a passenger behind means that there are less than 5 no-shows, or that there are 4 or less no-shows, so the probability of x being smaller or equal to 4. Let us find this probability using the calculator. We need again this distribution. We need the binomial CDF, which is the 5th. We want just for a single value to find the probability. The number of trials, well, we have 115 passengers. They are the trials. The probability of a success, this means of a no-show, is 0.07, and we're interested in this number of no-shows to be smaller or equal to 4. So let us calculate the probability, and we get 0.089, which is 8.9% and hence more than the 5%. So this shows that booking 115 passengers are too many, and obviously the airline should book 114 passengers on the flight.